we are live.
Yay, we're live. We did it at this
We
weird
did do
time. I'll be amazed if we have anybody watching us. What? There's 26 people watching us.
We do, and we have another 18 people over on Twitch, and it is excellent. It is excellent.
Mm-hmm.
So thank you, everyone. I'm just realizing I forgot to open up a new audio file after Daily Space. Thank you so much, everyone, for your patience on the on again, off again of this. I learned an important lesson this week. When you are sick, turn off all notifications. Actually let yourself be sick so that you will get better. I didn't do that. And so Monday I felt horrible, wanted to die. Well, not literally. I just felt horrible. And then we reset everything for Tuesday, but Monday I kept getting notifications. I kept getting alerts. I kept getting telecons.
Yep.
And I pushed through to respond to everybody who made inquiries because I didn't want to be the thing that got in the way of anybody else doing their work.
Yep.
And that made me the thing in the way of my own work because Tuesday I felt worse than I felt on Monday. And
right.
So yesterday I still didn't turn off all my notifications, but I did a much better job yesterday of not trying to push through. And thank you, audience, for giving me the space to do that on both this show and on Daily Space.
Yeah. We don't really know the meaning of, like, balance.
No,
exactly.
Although,
it's funny. I've been talking to a bunch of people about our hiatus that we do, which is coming up, by the way. Prepare yourself emotionally for this. And they're like, "Oh, I'm so jealous that you can do that hiatus." And it's like we do it at enormous cost. Like going offline for 2 months from all the live streaming. It hurts the algorithms. It hurt
everything hurts.
Everything hurts.
Yeah.
Except for our sanity. That's the one thing that we get back is going, oh, I don't have to seek out, feel stressed by finding internet. And it sucks that, like, you see how Twitch streamers just get ground up if they even take too long going to the bathroom.
Yeah.
I guess we're Twitch streamers right now, so no one's going
to
the bathroom the next hour. Don't go to the bathroom. But it's really rough, and the YouTube algorithm forces you down that pathway, and everything. And even though they're saying like, oh, there's all these videos they have like, oh, you should take a break, you should take it easy, and no, like the YouTube algorithm is okay with you posting videos every few months.
No,
as long as they're 2 hours long and incredibly shockingly good.
Everyone has to go viral. If every single one of those videos posted every 2 months does not go viral, you are kicked out of the algorithm.
Yeah, it's rough. So I think that, but I choose my sanity over. I mean, it's a holiday, but where nobody does your work while you're gone, and you have to put the pieces of your business back together at the end of it.
We get punished for going on hiatus.
Yeah.
And
which is unfortunate. And I don't know what the, and this is sort of like another like rant, and people want to get us talking about astronomy, but people are talking about this idea of like, well, we should have a 4-day work week. But like that would be great. And for people where their work is very set and specific, and they come in every day and they do their work, and then they can have one extra day off, and the companies will handle it, no problem. But for most companies, all that means is that they're going to give you 5 days of work in a 4-day work week.
Yeah.
That the rules about work haven't changed, and it's just going to cause more stress. People are just going to be more overwhelmed.
So one of the interesting things they're finding is the companies that have switched to a 4-day work week are finding that people use their time much more efficiently and accomplish the same amount or more. And I don't
Sure.
know how much of that is because they are so stressed out that if they don't accomplish everything, they'll have to go back to a 5-day work week.
Hmm.
But yeah,
Yeah, and so like
it's
obviously there's like a little bit of slack in the system that you can tweak out. But anyway, are those the new glasses?
these are the new glasses.
How's it
I
feel?
have. It's weird because they're progressives. I went from not glasses to progressives because both far got fuzzy and near got fuzzy, and only things in the middle worked. And luckily, for the most part, my monitors were all perfect. But I realized when I put these on that it was like going from 1080p to retinal,
Yeah.
and so while I could still see everything, I could now see things better.
Yeah, it's time for me too. I'm doing a lot of, this as I, you know, Carla would go, "Look at this," and she'll show me her phone and I'll be like
Yeah,
pushing it back.
yeah.
So it's time.
Did you ever play Magic the Gathering?
Sure.
So Lindsay, my PA, plays it avidly and got me back into playing. And I couldn't read the cards. And
No matter
so,
how far no matter how far you went.
well, some of the cards have such tiny print on them that they'd be
Yeah.
completely in focus at this distance. And now the text is too tiny. It has too small an angular
Yeah.
size.
Yeah, on a bad background. Yeah. Yeah.
Yeah, yeah. And so it was kind of self-defense against her elf deck that I
Right.
needed to be able to read what was about to happen to me. She still
That's
wins.
awesome.
She still wins.
All right. I think it's time for us to do our jobs.
It's true. It's
Um,
true.
so let me know when you're ready.
I am going to press record on the video first. I'm now pressing record on the audio.
Okay.
Testing. It is recording.
All right. Here we go.
All right.
Astronomy Cast, episode 637, Machine Learning in Astronomy. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today, and with me, as always, Dr. Pamela, senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. I have given in to presbyopia and I have gotten glasses and
Yeah,
as someone put it, the trees, they now have leaves.
I'm ready. I'm ready. It's my time as well. I think I can. There's only so far my arms will let me,
Yeah.
stretch my phone away from my face. Yeah, yeah. Getting old
But
sucks.
presbyopia is such a cool word. So if you're going to have something go wrong, may it at least have a really cool word to describe it.
Right. Yeah. If only all medical and I guess age conditions were like that.
Yes.
Computers are a big part of astronomy, but mostly they've been relegated to doing calculations. But recent developments in machine learning have changed everything, giving computers the ability to do jobs that humans could only do in the past. And we'll get into it in a second, but it's time for a break. And we're back. I guess it's not that surprising that computers, machine learning specifically, are starting to show up across the field of astronomy. Computers have been tied in so closely to everything that astronomers do that it's just a matter of time before the artificial intelligence shows up to really run things.
Well, and it's getting to the point where the rate at which we're acquiring data is growing exponentially.
Yeah.
And the number of astronomers in the field is not growing. And so, since we don't have more astronomers to deal with all of the data, we've really got three choices. Students, again, not enough of them. The general public, and we do totally use the general public. Go listen to one of our go listen to one of our episodes on citizen science. But again, not enough of them because
Mhm.
exponential growth. And this is where we have to turn to computers and hope that processing speeds continue to grow at a rate that allows us to keep up with that flux of data.
Now, it it's funny. You are uniquely positioned to talk about this situation because you have been at the forefront of citizen science, of identifying things that computers can't do that humans can do and are happy to do or will begrudgingly do if let them know that the science is important and Bennu's
Yeah.
rocks really do need to be mapped. But
Bennu.
Bennu rocks. But just this idea that there's things that computers are really bad at. And so let's
Yeah.
organize a whole bunch of human beings to do the things that humans can still do that computers can't do. Is that landscape starting to change from your perspective?
It's changing in terms of how we are interfacing with volunteers. Once upon a time, back in the days that the Galaxy Zoo project entered the battlefield of human versus data set, there was an issue where the Sloan Digital Sky Survey had so many tens of thousands of hundreds of thousands of galaxies in it that there was no way poor Kevin Shvinsky was going to, as part of his dissertation, get through hand marking all of the
Yeah.
galaxies without madness occurring.
Right. It was a job
And
for grad students, but
yeah,
still, there weren't
and
enough of those.
and at that point in time, software was nowhere near being capable of being trained to mark galaxies. This was about the point that one of my colleagues, when she was working on her dissertation, back in the days of MySpace and LiveJournal, posted something along the lines of, my software has discovered that wherever there are lizards, there are sailboats, except sometimes they're mountains. Because the training set for the software, it turned out, where they were marking lizard, 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 the training set, all the triangles in the training set were sailboats. Except when they got to other data sets, there were triangles that were mountains. And so we don't always know what we have used to train our machine learning algorithms, and they can make fabulous mistakes.
Right.
Wolves are dogs that have snow around them, became the results of one algorithm.
Right.
And so at that point in time, we couldn't get software to say, this is a galaxy and this is what the galaxy is doing. Now, luckily, with the advent of better and better processing, and more importantly, the advent of cloud computing, we are able to spin up special systems that are designed to learn better, faster, not cheaper. They're so expensive, but better and faster by taking the training sets from human beings and saying, okay, based on this, I actually now have the capacity to figure out what galaxies are. So now, instead of having strictly the human being saying this is a galaxy that is behaving in this way, the software goes through and goes, this one is shaped like this one is shaped like this one, low probability on my understanding it, kick it back to the humans. So the humans are now the trainers and the fixers. And this frees up the humans to work on solving more and more problems. And this is useful because there are some problems like we had with Bennu, where the entire data set that you need to classify to, in this case, find a safe place for OSIRIS-REx to boop an asteroid, the entire data set wasn't big enough to train an algorithm. So the humans had to do the entire thing. But when the data set is big enough, now the humans just train it and then fix its mistakes.
So let's talk about, like, fundamentally how machine learning works, and then sort of how it's used in astronomy.
Machine learning is very much a black box. Even the people who do machine learning, although some of the latest articles are hinting at new ways to look in at what the computers are making their choices off of. But the basic idea is there are algorithms that when you show them an image that has the thing that you are interested in the image. So you have to divide things up into stamps for the software still. So you divide it up, and the software then looks at your image and says, based on the 10,000 to a million images like this that I've looked at, I am going to say it's doing facial recognition on a human, look at the separation of the eyes, the eye to chin ratio, and look at all these different things and identify who is in the image, what is in the image, and the places where we still run into trouble. And machine learning gets used for many other things. I'm focused very, very narrowly on computer vision right now.
Mm-hmm, mm-hmm.
Where the software still struggles is we can't just give it a mosaic of the moon and say, go forth and find all the craters. We have to instead identify all of the craters through some other means. And then once the craters are identified, try and get software that will correctly identify the edges of the craters. And we can still only get that at the 90-something% accuracy level, which isn't good enough for a lot of what we'd like to do.
Yeah, and like underlying like the way these algorithms work, and I mean, you know, there are whole podcasts that go into how machine learning algorithms work. But generally, you've got a neural network, and again, that's a whole other conversation, that you are teaching it how to do various things. And so you show it a picture and you say, this is a crater. And then you show it another picture and go, this is a crater. And then you show it a million more and go, these are craters. And that's sort of one part to it. And then the other part that sort of has really kind of taken off is this idea of an adversarial network.
Yes.
So you have one computer whose job is to recognize craters, and then another computer whose job is to tell whether or not the first computer is doing a good job of recognizing craters. And so one is good at generating something and the other one is good at recognizing something. You can set those two against each other, and that's how you get those, like, you know, human faces generated by artificial intelligence with these generative adversarial networks. But just in general, it's this process. And as you say, it can be, if you're lucky, it can be automated, but it's almost never, you're never lucky. And it's always a human being is patiently explaining to a computer, this is a crater. This is not a crater. This is a crater. Do you see the crater over here, computer? This is a crater. So,
and
so
the
humans are deeply involved in this process.
And the reason that craters are something that it struggles with so incredibly much is because soils can be completely different colors from one place to another. You can have varying shadows, and the soil can be different textures. And computer vision has to be given a training set as diverse as the population it's eventually going to be working on. Twitter ran into severe problems with their image algorithm, where if you give Twitter too large of an image in one aspect ratio or another, it's going to only show the person in your Twitter feed a section of that image. And they have a really good algorithm for figuring out where the face of a white person is.
Right, yeah.
And it's not
so it's garbage in, garbage out.
Yeah. And so we have to be cognizant of good data sets in. So to return to the lunar problem, if you go through and you do an excellent job marking every crater in an Apollo region, well, it's either going to all be mare or all be regolith, which means it's all going to be dark soil or light soil. And that algorithm's only going to be able to work on that particular kind of the moon during that particular lighting condition. So getting a diverse enough training sample can be hard for some problems.
Yeah.
Other problems, it's super easy.
We're going to talk about this some more, but it's time for a break. And we're back. It's funny that concept of like having a difficult time also changes even if you change the parameters. Like if you take a
Yes.
picture of a dog and you rotate it 90 degrees, so now it's a dog on its side, the computer just goes like, I don't know what I'm looking at here.
Right.
What is this? Where's the dog? There's no dogs in this picture. And then you rotate it back and like, oh, there's the dog. I see it. But those kinds of sort of image translations are being done now as rudimentary part of this machine learning. So they're getting better and better. All of these issues that we're talking about are getting better and better and better. And I think, the reason we queued up this episode, this topic, is because it does it. I don't know how it feels to you, but it feels to me like we are shifting into from them being more of a pain than they are a help, and us really wanting to have humans do the work, to us shifting into this hybrid model where they're pretty good when you've got humans that know what they're doing to train them. And now we're getting some really amazing results out of these machine learning projects.
And it's that combination of they're finally giving us really good results. And with LSST coming, it's kind of like machine learning is our Obi-Wan Kenobi. It is our final hope.
Yeah.
And the diversity of problems that are being approached with it, we have not just the galaxies and that still doesn't work correctly, craters, but we also have things like looking at light curves and finding exoplanets. We have figuring out comets and asteroids as transient phenomena, identifying supernovae, space weather. We have this amazing suite of solar observatories coming online and online right now. And solar storms, as some of you in the past week have been able to see, generate amazing light shows in our sky that can also do really bad things to our power grid and satellites in orbit.
Right.
And machine learning is helping us understand that space weather.
Yeah, we had the auroras here last night. It was, but they were hidden behind cloud. And so we could see the green glow peeking through the clouds and
That's the
purple
worst.
and stuff around it. Yeah, it was rough. So let's talk about this idea. So you gave a great example, this idea of, say, exoplanets, of recognizing exoplanets. And so having a human being look at a light curve, we've always said that we can teach a 4-year-old how to recognize a crater, right?
Yeah,
But
yeah.
it's really hard to get a 4-year-old to recognize the light curve of an exoplanet. So how, for example, has machine learning been able to really make an impact on that kind of a research?
The human eye is troubled by noise and can both see false signals in noise and also miss actual signals in the noise. So say you have data coming down from a star that has sky brightness fluctuations. We're using satellites, that's a bad example. Say we're looking at a star that has a lot of sunspots on it, other things that may be causing noise in its particular light, but it also has a planet that's going around and around within that noise. Well, the computer will have the ability to see there is always this exact same looking dip over time that is repeating over and over at the exact same interval, that while it may not be that different from the noise, it's always there, and that's a planet. It also just relieves all of the people who otherwise could be doing other science from having to look at data that isn't perfectly clean. Classic algorithms were completely fine going, the star is constant brightness, it dipped X% and then became constant brightness. Classic algorithms, I could write that code in 2 days. To deal with messier systems, to deal with multiple planets, to deal with noise, you needed humans, and they were still imperfect. And the algorithms are still imperfect. But between both of them, we're going to find everything.
All right, we're going to talk about this some more, but it's time for another break. And we're back. Now, you sort of introed into this video just talking about the enormous amounts of data that are coming online. And it's really hard to understate how significant this modern age of astronomy, these giant observatories connected with huge fiber optic cables to the internet, and will just be disgorging their data onto the internet by the exabyte.
Yeah.
Like the Vera Rubin telescope. I forget.
Yeah, it's Vera Rubin Observatory doing the LSST, which is the name of the survey. And so I can still say LSST. It will always be LSST. So LSST is going to be returning petabytes of data per day as
Per day.
yeah. It's like Cisco Systems is designing special systems for this scope.
Yeah.
And they are expecting, they're not entirely sure of the order of magnitude, but between tens of thousands and millions of transient phenomena. These are things that flicker, flare, pulse, move, or otherwise are not constant in the data set. And that's going to be comets, asteroids, which were one of the major motivations for building this scope, supernovae, Bielac objects, which are galaxies that flicker in brightness, regular pulsating stars, cataclysmic variables.
Planet 9.
Planet 9 is my deepest hope. I need that world to exist. I need that world. And with a machine learning algorithm, we can feed the system, okay, here are 100,000 objects that we already know about, that we have tortured people with the Sloan Digital Sky survey, with the Dark Energy survey, with all the precursor surveys. Here, computer, is what these known objects look like.
Yeah, and in terms of like spectroscopic information, in terms of visual information, in terms of
how they move,
time, domain, how they move, how they change in brightness, all that kind of information. Thanks, humans.
Thanks, humans. And then one of the nice things about looking at the sky as opposed to looking at the surface of a planet is we've had for decades algorithms that go through and say, light, no light, light, no light, and can look at the distribution of the light, and all stars are point sources. And their light is smeared out in a way that is dictated by the optics, and if you're using a planetary scope, by the atmosphere. All the stars will have the exact same shape on your image. And anything that doesn't have that shape, that's going to be a galaxy, a nebula. Occasionally quasars can get misclassified, but LSST is so big, I'm not really worried about that right now. And so the software, the dumb software we've had for decades, can go light, no light, and then go star, not star. And then the machine learning algorithms can look at all the not stars and go galaxy, planetary nebula, supernova remnant. I'm waiting to see how they differentiate those two.
Right. Asteroid, comet.
And then the things that it can't classify within a given percentage of probability, those can get kicked out, and some of those will be completely new objects we've never seen before. And once we've seen 100 of them, then we train the machine learning algorithm more. LST is going to have so much data that we're going to be able to train machine learning algorithms with a sufficiently large data set that we're going to be classifying things we don't even know about at this moment while we're recording this episode.
It's funny to think about that it's going to be recording just so much data about the sky that it will have a giant record of a class of object that we didn't even know exist. And some astronomer will look through it and go, what's this? And then the algorithm will go, oh, you're interested in those things, huh? We didn't know what they are, but here's 10,000 more. The astronomer will be like, oh, thank you, computer. Thank you. This is my career now. Because it's going to be crazy. It's just going to be mental. And there's no way to do this without artificial intelligence, without machine learning, that is going to be grinding through these images one after the other and just identifying everything that's going on inside of them. Like it would be hopeless.
But the other side of this is the citizen scientists or grad students or undergrads or whatever human beings are training those algorithms, they're just going to be casually looking through objects we've never seen
Yeah.
before and helping us figure out what they are as the wetware that goes to our software that allows our hardware to have its full potential.
Oh, yeah. So what do you think is the limit? I mean, again, you run a citizen science organization getting citizens to help with astronomy. Where do you see the future going over the next couple of years as these computers continue making leaps and bounds and the data that they have access to is getting more complete and more machine learning friendly?
I don't see a limit, because over time what's going to happen is those things that are very short-lived in the sky that are fairly rare are going to take years to track down and figure out. We're just starting to figure out what fast radio bursts are.
Mm-hmm.
We are just starting to figure out that there are these weird snakes that are visible to Meerkat in the center of our galaxy. And it's going to take, well, the entirety of the human future to see all the different things our universe has to offer us in statistically significant numbers.
I guess it's like the rarity, right? And maybe we're
Yeah.
chasing Pokemons or something. Or we're putting up magic cards. We've got all the common and the uncommons, and
And the mythic rares.
now we're looking for the mythic rares, and they will be disgorged. But there'll be these weird objects, and there'll only be one every year. And astronomers will
Yeah.
figure out that, oh, that's a situation where one star ate another star and then they were consumed by a third star. And
Yeah.
that's how you
Yeah.
get that really weird flash that comes together. But by analyzing those, we will make these fundamental understandings about how the universe works. Oh, this might be why supermassive black holes got so big so early. This might be how the first stars were able to form. This might be what the universe is really populated with in between galaxies, that the one-offs and the weirdos tell us about the science as a whole, which is fantastic.
And the thing to keep in mind is 99% of the time that the software rejects something, it's because, like, you have a comet superimposed on top of a galaxy and the software is like, I don't know. Or you have two galaxies superimposed on each other, or it's gonna be something where it's completely normal objects that are configured in a really weird way.
Yeah.
And human beings can look at that, and it's like those optical illusion photos that it's something normal and your brain initially interprets it as weird. You can figure it out. But that small fraction of the time is the reason you keep doing this, because you might find, well, Hanny's Vorverb.
So don't worry, humans, you still have a role in the field of citizen science astronomy, but just don't be surprised if your time is spent teaching a computer to do your job, so that you can find even more interesting projects to teach even newer computers to do that job as well. I like it. I think, let's let the computers do the digging through petabytes of data to find
part.
the tedious work. Let's do the fun part. Awesome. Well, thank you, Pamela.
Thank you, Fraser. And now I have to say thank you to so many of you out there. This show is made possible by you, and by the fact that you allow us to pay Rich, Nancy, Beth, Allie, all the folks behind the scenes to herd us like the cats we are and keep track of all the craziness that we sometimes introduce into scheduling and things like that. This week, I want to give a special thanks to Blixa the Cat, Dean, Claudia Mastriani, Connor, John Drake, Nyla, Bart Flaherty, Brian Kilby, Corrine Dimtruk, Tim Gorish, Arctic Fox, Lou Zealand, Lee Harborn, Mark Phillips, Kathleen Matson, Bob the Boodle Cat, Chris Wheelwright, Jason Corducas, Olivia Brain Zank, Ron Thorson, Papa 1062, Robert Hundy, Kim Barron, Vitali, Paul Esposito, Gordon Turner, Arthur Latz Hall, Frank Stewart, Ganesh Schwamithan, Bob Bob Zatsky, Reuben McCarthy, Jeff McDonald, Iggy Hammock, Rebecca Gold, Killian and David Parker, Scott Briggs, Roland Vormerdam. And if you too would like to be part of our amazing and vibrant Patreon community and potentially have me mispronounce your name, join us on patreon.com/astronomycast. And you can actually put in a pronunciation guide. All of you starting to do that. I see you.
Don't
I
do
love
it.
you.
Don't do it. I love it. All right.
So, thank you.
Thank you, everyone. We'll see you next week.
Bye-bye. There are literally people putting in pronunciation guides, and they are my favorite humans. You are my favorite dog.
I deeply enjoy you attempting people's names. There's something wonderful about it. It is funny how, I mean, we're just getting access to just humanity around the world, and we're all interacting, and like one of these pieces, us getting very comfortable pronouncing names from various languages. Like, again, as I've been studying Chinese, I'm getting a lot better at pronouncing people's names.
I'm an equal opportunity destroyer of words. Basically, if I can't easily see where the syllable break,
see the Chinese characters, I don't know.
We occasionally have to drop the Cyrillic into our daily space episodes because otherwise I will not say things right. And even then, there's an SCHCK, all one sound, and I destroyed an astronaut's name.
Is that like Shkadoff thruster? Is that the sound?
Yeah.
The word? Oh, cool.
Can't consistently say it.
Right. Yeah. Well, I mean, part of it's like it's just like we don't have the mouth muscles.
Yeah.
Like we just haven't built up the mouth muscle training. And there's an interesting like practice that you do called shadowing, where you will play a piece of audio from someone who's a native speaker, and then you will attempt to follow them just beat for beat, exactly, trying to, and then you will even like play your audio next to their audio and hear all the mistakes that you make, and then you try again to fix it. And after a while, your muscles, you're building up new muscles in different ways that then you can more easily make these sounds.
Yeah.
And it's a funny thing. Okay, we got a pile of questions, and I think but there's a big theme here. So people are asking about telescopes and eyeglasses. So what are the rules for telescopes and eyeglasses?
So if you don't have an astigmatism, if your eyes simply focus at a different point, ditch your glasses and use that little focus knob. You're going to have a brilliant experience. If you have astigmatism, no amount of playing with the focus knob is going to fix that. And so you just need to wear your glasses, and it's never quite as good an experience. And I'm sorry, because I too am one of those people that when I look at lights, I see that diffraction pattern. I thought that was what everybody sees. And then I was
Everybody
corrected.
sees a spectra when they look around.
You know.
Yeah. I learned that my dad has astigmatism, and so always has had glasses since I was a kid. And one of his glasses is just, or was just, a piece of glass, and then the other one was a lens that he used because the eye had astigmatism. And so he would, he taught me about this with the telescope, and so it's interesting. But yeah, so that's it. So same thing with binoculars.
Yeah.
If you have astigmatism, use your good eye. If you have astigmatism and then just focus manually. If you're nearsighted, farsighted, take your glasses off, focus your telescope. And if you're using binoculars or both eyes have astigmatism, then keep your glasses on.
Yeah. Yeah.
And clearly you will know the telescope just for yourself, like the Hubble Space Telescope. You probably could, couldn't you?
I'm sure that you could get specialty eyepieces that corrected for your astigmatism.
Yeah.
I'm not sure. Like, I feel like this is the kind of thing that if you went to Teleview, they would say, challenge accepted, and then ask you for $100,000. So,
right. Yeah. Exactly. Okay. Arjun asks, could the AI be trained on old data, or will that
Oh,
happen
yeah.
after the AI has been trained by LSST for a few years?
No. So one of the things that they've been working on is training the algorithms on synthetic versions of what they expect data from LSST to look like, where they're using either SDSS or DES, dark energy survey data, so Sloan Digital Sky Survey or dark energy survey data. Um, and and the nice thing is, because there are all of these objects with known positions on the sky that we know what they are,
Yeah.
we can take the data and then we know what those things are and we run that. So it has its own training set as well. We run that through the algorithms and we don't have to reclassify anything. We just apply the existing classifications to the new images.
And you are seeing some examples of old data being fed into new algorithms. So the
Mm-hmm.
algorithms have been trained in one field over here, and then they go back to old archive data, pull it off the tape for Voyager's
Oh, yeah.
mission past,
Processing.
right, and then they'll reprocess the data using the modern algorithms and
Yeah.
find new information. So as long as you've got the data available, there's always a chance that you can just go back around and feed them to your computers.
Yeah.
Um, Hal McKinney asks, where do all the big telescopes store their data? How do you know if you find something new?
Uh, so in theory, um, when you find something new, you simply look up old surveys to see if it's visible in that. And if it is visible in that, then you look up to see if anyone published anything on that RA and deck position.
There. That
Sinbad is
so
kind
that
of the. Go ahead.
oh just that was the key, right?
Mm-hmm.
Is that every object is going to have a unique position on the sky, a
Yeah.
right ascension and a declination. And so you can search the web archive for that right ascension declination and see if anybody else is referencing that same object.
Yeah.
So if it's something that's moving, you can go to the Minor Planet Center and you can track all the various known asteroids and comets and so on. But what about the where are they storing it? So where's this data being stored?
All over the place. um, so the Canadian Astrophysical Data Center is one of my favorites. There is the Planetary Data Center, which is a whole bunch of different nodes all over the place that each have an entirely unique and not always intuitive interface. There is the Hubble Space Telescope MAST. It's their archive. I forget what the M
Yeah,
is.
was historical the Hubble anyway. There's an archive
Yeah.
for the Hubble Space Telescope. Yeah,
Sloan has its own archive that you can interface. It has one of the nicest interfaces, partially because it was like paid for by people who appreciate computer science. Always fund hiring actual computer scientists. I may have strong opinions.
yeah.
Yeah, so it's kind of all over the place. The clearinghouse of links to get to data is for many things, but not all things, because there's always exceptions, is Sinbad. So you can look up, type in M31, it will give you every single different categorization and name for it and point to a bunch of different publications. And so Sinbad is kind of the database we use to cross-reference everything, not moving things.
My trick is that you just search for telescope and then just search for raw data. So
Yeah,
you can search for Curiosity raw data or Perseverance raw data or Hubble raw data, and then you will get a bunch of links taking you to the raw data. And in most cases, there's an amazing portal for the European Southern Observatory that you
yeah,
can see pretty much everyone who's ever used their telescopes and everything they've observed, and even see the pictures that were taken so that you can use it for your own purposes. Um, it's all out there. You just have to
yeah.
search just raw data and then the name of the instrument that you're looking for, and you'll get pretty much buried in data. There's a
And
few times when they don't release the data because there's an agreement that the scientists get to publish first, and they
proprietary
get
period.
yeah, but it's usually fairly short, and then the data just starts to disgorge out.
Yeah. Architufus over on Twitch says MAST stands for the Barbara A. Mikalski Archive for Space Telescopes.
There you go.
So that's the one that's at Space Telescope Science Institute. It has Hubble, Spitzer, all of those different space telescopes. And the M is a person, and I would never have figured that out. So thank you, Arctitufus.
Yeah. Helmakini asks, what are the most astronomy enthusiastic countries?
There's research on this, and I'm trying to remember the
Oh, there
results.
is?
Yeah,
Wow.
there's IAU does research on stuff like this. What's interesting is the US is kind of unique in the fact that amateur astronomers are predominantly of the gray-haired variety. You find a lot more very young astronomy lovers in other countries. And I remember that Iraq had a much larger amateur astronomy community than I expected. Unfortunately, that is not an entirely useful amount of information. That is just what is stored in my head. There's research on this. I don't remember the results beyond being surprised at how many amateur astronomers are in Iraq.
Right. Arjun asks, do university astronomy departments collaborate with their computer science departments for this kind of work?
Not as much as you would want. Not nearly as much as you would want.
It's funny. You would definitely expect to see these collaborations, but in many cases, the computer science people are working on pure, like there's two kinds of computer scientists. There are like the pure computer scientists who don't actually work with computers, which I know is going to sound super weird, but they've learned how to program and they've learned how et cetera, but really they're working on algorithms. They're working on proofs. They're doing Turing style proofs or von Neumann kinds of proofs via mathematics, and figuring out what is the most optimal algorithm for finding a map, for navigating on a map or things like that. And they actually spend very little time on computers. And then there are the people who are becoming programmers, and often they're gearing themselves towards getting a job at Google or Facebook or one of those kinds of things. And I've just found that most astronomers have had to learn to become really good with computers, programming, data analysis, databases, storage, etc., as opposed to there being these kinds of collaborations.
The other side of that is money too, and I think that's actually the bigger barrier because like one of the situations I ran into is all of my graduate students, except for one, over all of the graduate students I've had, no, two. I've had two graduate students that were not computer science or otherwise worked in their major. So I hired a project manager out of the business department, but any student I had writing software came from computer science because it was easier for me to teach a computer scientist to write code to do the astronomy I needed than for me to train an astronomer to write fast, clean, sophisticated software. And this led to a lot of negative emotions because I was providing work for graduate students out of a different department instead of out of the physics department I was in. And so there were physics students who didn't have jobs. And that just leads to you aren't supporting your own humans, but the work required the computer scientists, and the computer scientists that I hired to write code went off and got jobs at
Google and Microsoft. And
there was an amazing press release that came out of, I think it was either Caterpillar or John Deere. I'm terrible. I can never keep the two companies apart. Whichever one is in Peoria. It came out a couple months ago about their new self-driving farm vehicles for harvests. And that actually came out of the department of one of my graduate students, who's now like vice president at a new startup. And it's just amazing to see what these humans who got their start writing real world code with science applications have gone on to do. And yeah, it comes down to an argument over, do you support your own students or do you hire students elsewhere? And I made the choice that was right for my research.
Yeah.
And there's no jobs, so I have no guilt about reproducing astronomers who will have no jobs. No guilt.
Yeah, and unfortunately, like from those two fields, like a person who goes into computer science, as long as you do well and don't wash out, you're guaranteed a good job, like a very good job when you come out, and a chance at like 6-figure salaries right out of college.
Yeah.
Or even with a couple of years of experience.
And
while
PhDs.
We know that. Yeah, and yet we know for astronomers, you can have 100 PhD astronomers fighting over one mediocrely paid position.
Starting salary is often around $45K.
Yeah, which is crazy. I pay people more than that for people who have no degree and they write for astronomy. Like they just write articles. So it's tough. And so, we always, which sucks because here we are getting people enthusiastic about space and astronomy.
But once they're enthusiastic, they can get involved in all these other ways that we're talking about.
Yeah.
We wouldn't be here if those computer scientists had been, hey, what if the Worldwide Telescope, which is now being used as one of the major ways to access data, came out of Jonathan Fay being like, I want something to better use my telescope. And he was at Microsoft Research, and he created it as a computer scientist, passionate about astronomy. And so we need more of these people that are specialists in other areas to take their enthusiasm and help us poor academics who can't afford those people to do our work as volunteers. Thank you. We love you.
Yeah. All right. Well, we've reached the end-ish of our time, and I've got to go do another meeting. So I think I need to wrap this up. So thank you, Pamela, for doing this episode with me. Thanks to everyone watching us, both on YouTube and on Twitch. Thanks to all the moderators for keeping the peace. And thanks to Nancy Graziano and the rest. Man, who are the people who are doing all the editing? Richard Drum,
Ali Pelfrey, Beth does our website. Beth Johnson does the website, and Nancy herds all the cats.
Yeah, exactly. All right. Well, thank you, everyone, and we will see you next Monday at our regular time, assuming Pamela doesn't get sick.
I was so stupid. Yeah.
All right. We'll see you then.
Okay. Bye-bye, everyone.